Okay, one more example before we move to more complicated boundary condition. Let's say consider a beam that is fixed to the wall again, and this time it has a lot of different kind of loading. For example, 1K, or simply let's call it 1 right here, and a couple moment here, 0.5 Newton meter, and a vertical load 3. So in this case we have all sort of different kind of loading. One distributed load to the right, one coupled moment exactly in the middle, and one vertical force just before the wall, and the beam is fixed to the wall. Now we want to find the moment diagram using Heaviside function. What we expect is just one single line that expresses the moment diagram. Alright, so in order to do that, I want to show the distances. Let's say this is 0.5, 0.5, and 0.5, and from here to here, let's say is 1 meter. So everything is given. Before I do that, I want to find wall reaction. So I take the entire thing as my system, and then I go ahead and draw FBD. So beam here, let's call this point A. So I'm gonna have AY, MA, then 3 right here, 0.5 right here, and I can replace, because it's an external load, I can replace with this point load acting as the centroid. The point load is 1, its magnitude and location is exactly in the middle, so it's magnitude 1, and the distance from here is 0.5 to the right. Now I'm ready to write the equations of equilibrium and find my reaction. So summation of force in Y 0 give me AY plus 3 minus 1 is equal to 0, and summation of moment was point A is 0, so I get MA positive plus 3 times 0.5 positive negative 0.5 couple moment, and then negative 1 times the distance, and the distance is from here to point A. So let's compute that distance. 1 to here, 1.5 plus half is 2, so that distance is 2 meter. Okay, so I should write here 1 times 2 negative is equal to 0. Now let's solve these two equations for reactions. This is going to give me positive 2, and then AY is negative 2, take it to the right, and for moment MA you get MA plus 1.5 minus 0.5 minus 2 is equal to 0. So 1.5 minus 0.5 is 1, minus 2 negative 1. I take it to the right, MA is 1 plus 1. So here I can just simply put these reactions in a wall. So AY goes down. AY goes down, and its magnitude is equal to 2, and MA is just simply like that, 1. And then I can get rid of all this calculation right here. Okay, I wish I had a bigger eraser. Let's see how it works. It's not very fast. Okay, it takes some time to erase these things. Alright, so I'm just ready to do my heaviside distribution. So here, what I do, I don't forget that before you actually do the heaviside, you have to put the distributed load backs. So here I have one point load at the very end that was substituting this distributed right here. So I just put this distributed load back. So let's just get rid of these things here and put the distributed load back, because we're going to cut it. We cannot just replace it with point load. We're going to cut it at somewhere in between. So now I can go ahead and do my cuttings. I take a point from left as a reference, and then I cut it to the very end point, such that I'll cover all kind of loading. So I call this X. And now for this, if I want to draw FVD, I will have one system from left and one part from the right that we don't really want to use it. This is the one on the right. Well, I just want to draw it to show you how the distributed load is cut. So here, let's just do everything with the black. So here is a part of distributed load, and there is another part remaining on the right. Okay, and you have MX, VX, and VX goes up on the right. These are default positive directions. MX goes the other way. And this load is included. And then you have a 0.5, 0.5, 3, and it goes down 2, and the couple moment is 1. There you go. That's all we have. And the system is equilibrium. So I consider this system on the left. So I do nothing with this part on the right. Okay, this is one big source of confusion for the students. Like if they have force here, like let's say another 5K here or another couple moment here, they will include it in the system on the left, which is not right. It's just basic vector statics, because our system is the one on the left. Okay, now just go ahead and write the moment equation about point X, summation of moment about point X 0 on system on the left. Don't forget this important thing. Then you get MX, positive, VX eliminates, and then you have to multiply this distributed load by its moment arm. So now this distributed load is external to the system on the left, so I can replace it with point load. So let's go ahead and replace this with a point load. What is the area of this? Well, I know that from here to here is X, and from here to here is 1.5. You see 0.5, 0.5 plus 0.5, 1.5. So the base of this rectangle is heavy side X minus 1.5. And we have to use heavy side because if I go less than 1.5, there is no distributed load. So I have to make a switch to make it off. Okay? And its height is equal to 1 always. So the area under that is 1 times heavy side X minus 1.5. So let's replace this. let's take a color red and replace that with just point load at the center. The value of the point load is equal to 1 times Heaviside x minus 1.5, which is equal to Heaviside x minus 1.5, and its location is equal to the half of the base. So from here to here, this distance is equal to Heaviside x minus 1.5 divided by 2. So if I want to add it right here in this box, what should I write? I should say the moment arm times the value of the force. So the moment arm is Heaviside x minus 1.5 divided by 2 times the value of force. So the total thing becomes half of Heaviside x minus 1.5 square. So now we go to the direction. We take our right hand side, and as we can see, you see this is the direction of finger, the palm of your hand, and then it's going to be this way, so it's positive. That's the way you do the distributed load here. Okay, now the next thing is the couple moment in the middle. So in order to compute that and include it in the moment relation, I have to have some sort of switch that make it on or off when x is greater than 1 and when x is less than 1. So I say, because the couple moment is negative, I say negative 0.5 times Heaviside x minus 1 to the power 0. And we already talked about this switching mechanism in the previous videos. So in fact, when x is less than 1, there is no 0.5 couple moment, it's 0. And when x is greater than 1, you have negative 0.5 times 1, because x minus 1 to the power 0 is 1, right? So now the next thing is the 3. So for the 3, so I continue, write it in the next line. For the 3, I say 3 times Heaviside x minus 0.5 to the power 1, because that's exactly the moment arm for the force 3, and its direction is also negative. Now I go to the couple moment in the wall. There is 1 Newton force, so I say plus 1 times x plus 2 times x, because this force in the wall is 2 times x plus 1, and this is the couple moment, wall couple moment is equal to 0. Now solve this equation for mx. You get m of x is equal to negative half x minus 0.5 square. It just simply take to the right, and this Heaviside function, don't forget, when you take integral or derivative, it's gonna be act like exactly like it's gonna act exactly like parentheses. So you don't really need to have a separate mathematics for Heaviside function, how to differentiate, how to integrate it. You just treat it like parentheses when it comes to the basic math operation. So m of x is equal to negative half of Heaviside x minus 1.5 square plus 0.5 Heaviside x minus 1, 0, plus 3 Heaviside x minus 0.5, negative 2x, negative 1. That's your moment diagram. So in the exam, if I say draw the moment diagram, if you just come up with this relation, that means that you don't really need to draw it, because this relation includes the entire moment diagram. It's just in just one line. It's a compact notation. Now let's say if I want to find deflection, well, all you do, you know that the second derivative is equal to m over ei. Now again, let's take ei is equal to 1. Okay, so all you need to do is to double integrate this equation, plug mx negative 2x plus negative 1. And then you double integrate that. For example, the first integral, you get the slope dv dx is theta, the slope of the neutral axis. So you get negative 1, 6, x minus 1.5, 3. Why? Because when I take the derivative of this, it becomes negative 1, 6 times 3, x minus 1.5 to the 2. Okay, and 6 to the 3 is 1 half. So I get back to this relation. You just treat it to make it short, like a parenthesis, x minus 1.5, 2. How do I integrate this? X minus 1.5, 3 over 3. 3 multiplied by 2 gives you negative 1, 6. The second thing, 0.5, x minus 1 to 1 over 1, which is basically x minus 1. Let's erase this extra information. And then the next thing is plus 3, x minus 0.5, 2 over 2, negative 2x2 over 2, negative x plus c1. Apply the boundary condition. What is the boundary condition? Here, let's zoom. The slope, you see this in neutral axis goes like that. The slope, theta, is 0 exactly in the wall. That means dv dx is 0. Now if you put x0 there, you get c1 is equal to 0. Take one more integral, and then you get v of x, which is equal to negative 1/24 x minus 1.5 to the 4 plus 0.5 x minus 1 2 over 2 plus 3 over 2 x minus 0.5 3, and cancel out with this 3, so you get that negative x 3 over 3 negative x 2 over 2 plus c2. Apply boundary condition, you get c2 is equal to 0. So this is the equation of your neutral axis. So this is a composite relation. Don't forget, you always don't have this term right here. You only have this term when x is greater than 1.5. Similarly, you only have this term when your x is greater than 1. Again, you have this term when your x is greater than 0.5. But look, you always have these two terms right here. So your beam deflection plot, if you plot this curve, is a complicated curve. It's not just simply a first order polynomial all the time. Okay? So in the exam, I may ask you, give me the equation only between x, between 0.5 and 1. Just give me the equation only between 0.5 and 1. Well, you come and say, this is my master equation, right? That includes all the intervals. Now, I want to evaluate this v for x between 0.5 and 1. I go one by one. Do I have this term right here? Well, my x is less than 1, and therefore is also less than 1.5. So this thing is actually nothing here, null, is 0. So I don't have this. Again, I do the same logic comparison. I don't have this term, null, because x is less than 1. And here, yes, I do have this term. And this term becomes half of parentheses, x minus 0.5 square to the cube, third power, cubic term. And this term, I always have it, x squared over 2. So this is my equation of, and these are parentheses. This is not a Heaviside function. This is the equation when your x is between 0.5 and 1. Now, what is your equation when your x is between 1 and 1.5? Again, you go here, your x is still less than 1.5, so you don't have this term. you do have this term because x is greater than 1, right? So you have 0.5 to parentheses x minus 1 square, and again your x is greater than 0.5, certainly. So you have the rest of it plus half x minus 0.5 to the third power, and then you have negative x3 over 3, negative x2 over 2, and C2 is 0. You see, you can easily recover all the different equations just using a basic master-heaviside relation, which is right here. Let's highlight it one more time. This is the master relation that gives you all different intervals. And now you can see the power of heaviside function, how greatly simplify your job. All right, in the next video, now we go to the boundary condition. Finally, let's consider a case that so far we usually had, this is fixed to the wall. And the boundary condition for C1 and C2 was easy. Both of them were 0 because what? The derivative at 0 was 0. And for this guy, the deflection at 0 was 0. But what about the case like this? If you have a beam that, for example, this is pinned right here, and then this is roller, and now you have, for example, force here, 2, couple moment here, 1, and another force here, 1. What about this problem, this case? Now the boundary conditions are not really that easy, like this example on the top. Now in the next video, we're going to talk about example like this. I'll see you later.